I was owing you a description about money, and so that's what we're going to talk about first. Okay, so compound interest. So let's talk about money. Right. Suppose that you have $100 in your account, and the interest of this account is 8%. Okay? Question, how much money will you have in 1 year? This is the annual interest, right? So how much money do you have after 1 year?
400 times 1 plus 8%.
108. That's right. How do you know? Sorry? Okay. All right, so let's do this. So the answer is 108 after 1 year. How do you know? Okay, so first of all is we have to turn this percent into an actual number. As you guys might know, percent means by 100, right? So one part in 100. So 8% means 8 parts in 100, or 0.08. Okay? All right. So after 1 year, you have your original $100 plus the interest, which is 0.08 times $100. And that is equal to $100 multiplied by 1 plus 0.08. Or even shorter is $100 multiplied by the number 1.08. Okay, and that's $108. Great. So as you can see, the short answer is you take whatever amount you got in the starting, when you're starting, and you multiply it by 1.08. Okay? If we had started with $1,000, the same thing. $1,000 times 1.08, that's what you have after 1 year. Okay? So after 2 years, how much money do you have?
Square.
Okay, so I hear a square. So it's 100 multiplied by 1.08. Remember, this is now what you start with in the end of the first year, right? And 1 year later, you have this amount times 1.08. Remember we said, waiting for 1 year is equivalent to multiply by 1.08. So times 1.08, which is equal to $100 times 1.08 squared. Okay, so after, let's say we wait for t years, the amount of money you have, A of t, is equal to the original amount multiplied by 1.08 to the t. Make sense? So if A0 is the initial amount, initial amount, and P is the interest rate. In this case, it was 0.08. Then A of t is equal to A sub 0 times 1 plus P to the t. Same thing as we did over here. That's the formula for annual, for the standard compounding of money. Okay, now this is annual compounding. Annual compounding. By this I mean that essentially you have your money sitting around for a year, and only after the year is over, the bank comes and says, okay, I'm going to give you your interest, Chan, 1.08. But that's not really how it works, right? You can go to the bank, you can leave the money there for, I don't know, for a few days or for a few months, take your money out, and you already have a little bit more, right? Right? You don't have to wait for a year, right? So I don't want to dwell too long on this discussion because we don't have much time, but I will tell you the alternative to annual compounding, which is continuous compounding, okay? Which is a situation where you're earning money continuously, all the time. If you leave it there for 5 days, you'll make a little bit of money, but you do make some money, right? If you leave it there for 10 months, then again, you make some money. So that is a more sophisticated way of compounding money. Continuous compounding is calculated as A of t equals to A sub 0 times e to the pt, where p is exactly the same thing as before. These look like very different formulas, right? It looks like it's totally different. As a matter of fact, they're not all that different. Which one do you think is more, this one or this one? The second?
Yeah.
The second is more, yeah, it's a little more. Not much, but it's a little more. And remember we were talking about exponential growth, like bacterial growth or radioactive decay, things like that. It's exactly this formula, right? What were we calling the p before? It was the k, right? We used to call it a k. So now it's called p, it's the interest. Let me give you an example, and we're going to compute both annual compounding and continuous compounding. So that you can see that they're actually not that different. So you start with $1,000 and interest rate 10%. The question is how long before having let's say $30,000. $30,000 is a lot more than 1,000, right? You've made 30 times as much as you put in. So let's first do it with let's first do the continuous compounding because it's the easier ones. We've already done it before. So the formula is, like I wrote over there, is A of t equals A0 times e to the pt. And of course, A0 is equal to 1,000. We don't have to write the units anymore because we're thinking we agree beforehand we're doing everything in dollars. Times e to the, and what is p again? If we get rid of the percentage, it's 0.1. It's not 10. It's actually 0.1 times t. Can you see that in there? Yeah. More or less, right? Oh, wait a minute. Yeah, I should have done this. Sorry. Okay, is that better? Yeah, all right. So, okay. So how much time before having $30,000? What do you think? How do we do this? Set equal to 30,000. That's right. And then find out t, right? Okay, so after t time, and we're trying to find out t, or we can call this t0 time, a of t0 is equal to 1,000 times e to the 0.1 t0 is equal to 30,000. We're trying to find out t0. So what do? We solve for t0 in this equation. We can cancel out the 1,000 here and the 1,000 there, and we get e to the 0.1 t0 is equal to 1,000. Sorry, that's 0.1 t0. Okay, so we take logarithms on both sides. Oh, not 1,000. Sorry, not 1,000. Sorry, that's 30. Ah, you're paying attention. Sorry. Okay, 30. We take logarithms on both sides, and we get 0.1 t0 equals to natural log of 30. And this means that t0 is equal to, what is it the same? Is it dividing by 0.1 is the same as what? Multiplying by 10, right? Okay, and this is roughly let's see. When you compute this in the calculator, is roughly 34 years. It's not that much. Basically, it's the amount of time that you guys will take to retire. Maybe. Actually, it's less than that. If you start saving when you're 30 years old, at this point you can retire and make 30 times more money than you started with. That's pretty cool, right?
What about inflation?
What about inflation? Okay, that's a good point. Inflation will eat a lot into your money, right? If inflation is half as much as that, let's say 5% instead of 10%, then those same $30,000 are only going to be worth maybe, I don't know, 8,000 of today's money, something like that. So it's not as much as you would think, but it's still a lot of money. Eric?
Yeah, but our interest rates aren't 10%. They're like 0.5, 0.3.
You're absolutely right, Eric. The math doesn't work quite as nicely now that interest rates are very low. Long-term interest rates have actually hovered around these things if you look back a couple of decades, right? Right now, they might be just historically low and they might come up again, but who knows, right? Yeah, that's true. Okay. On the other hand, if interest rates are low, then you can borrow money more cheaply, and you can start a business and make more money that way. Okay, so let's do the same thing, but with annual compounding instead of continuous compounding. The formula for annual compounding, as we said before, is a of t is equal to a0 times 1 plus p to the t. Okay, where is a0 is 1,000, and this is 1 plus 0.1 to the t, which is equal to 1,000 times 1.1 to the t. Okay, so same story. At time t0, 30,000 is equal to 1,000 times 1.1 to the t0. So I can cancel out 1,000, and I'm going to cancel it right this time. It's 30 equal to 1.1 to the t0. Now, once again, we want to bring this t0 down, and we could take the logarithm in base 1.1. But I'm not going to deal with that. Instead, we're just going to take natural log, and you see how it works out just as well. Like, I'm going to take natural log on both sides, and I get ln of 30 is equal to ln of 1.1 to the t0. But as you guys know, or I'm assuming that you learned this in the class with Knut last week, you can bring down this t0, and this is t0 times log of 1.1. That means that t0 is equal to log 30 divided by log of 1.1. And if you do this in the calculator, this is roughly 35.7 years. Okay, so this shows a few things. First of all, it shows compound interest is faster than annual compounding. So you're actually making more money with the same interest rate. Okay, second point, they're surprisingly similar. If you look at the two formulas, you think these are totally different things. Why on earth would you bring up this e to the p of t? Where does that formula even come from, right? And as it turns out, the two formulas are actually quite similar. They only differ by like $1,000 out of 35,000, which is not that much. Okay, I'm just going to tell you real quick, even though we don't have that much time, how this formula comes from, where this formula of the continuous compounding comes from. Derivation of a of t equals a0 e to the pt. Okay, suppose that the bank makes a deal with you, which is a little funny. Instead of giving you 8% annually, let's break it down month by month. Okay? Here's the deal that the bank does with you. You break down 8%, you divide it into 12 pieces of, I don't know, 0.6% every month. And every month, we're going to calculate the interest. Okay? So instead of doing it every year at 8%, we're going to do it once a month, and the interest rate is going to be 8% divided by 12. Right? Is that the same thing as doing it annually once every year?
No.
It's not the same. And when I was in, middle school, I was surprised because it's not the same deal. You know, you're getting a different deal. So be aware that it's a different deal, but that's the deal, okay? Let's say that the bank does that with you. Should you take it? Actually, you should, because you're getting more money that way. Just a little bit more, but you're getting slightly more money. So, compound, instead of once in the year, compound n times in the year with interest rate P over n. Okay, that's the idea. It's to compound instead of once a year with interest rate P, compound n times a year with interest rate P over n. Okay? So, let's say you wait for 1 year. After 1 year, how much money do you have? Well, the starting amount, A0, and then it's the same thing as waiting for, let's say we do this month per month, right? So doing it in this way, with compounding every month at a rate of 8 over 12, is the same thing as compounding it annually for 12 years at a rate of 8 over 12. You see, because we're doing this whole thing 12 times with an interest rate of 8 over 12. So the number is 1 plus P over n, the interest rate, compounded n times. Right, we're compounding n times with an interest rate of P over n. Okay? So that's after 1 year. If I did this after t years, then it's very similar. Basically, it's A0, 1 plus P over n, and we're doing this compounding n times t times, because we're doing t years, and each year we're doing n compoundings, right? Great. So as n goes to infinity, meaning that instead of doing it every month, let's say that the bank does this other deal with you, let's compound every day. You break down the 8% in 365 pieces, so it's a minuscule amount every day, but every single day you get compounded, right? So n would be 365 instead of 12. Or you can do compounding even more frequently, no matter what, just n for n very, very large. As n gets very, very large, this expression a0 1 plus p over n to the nt, I'm going to do a trick. This is equal to a0 1 plus p over n, and I'm going to take this n and I'm going to divide it by p. So this is n over p, and I'm going to take that whole thing and I'm going to multiply that with p, and then t. Okay, so what did I do? I multiplied by p, I divided by p, and I brought this whole thing down on its own fraction, on its own exponent. Okay, the main idea is that when p is very, very large, this thing converges towards e. Okay, and that's something that, again, we didn't do in my class, but I believe you might have done it with Knut. Did you guys do this with Knut? That e is that limit? No? Okay, anyway, so again, we don't have that much time, but basically e can be written as the limit when n tends to infinity of this expression. So this converges towards a0 times e to the pt. So there you go. As the bank makes you an offer to compound more and more frequently, every month, every day, every hour even, the formula a of t becomes closer and closer to this thing. So that's where the compound interest formula comes from, which is pretty cool. And that's it. That's the proof. All right. Questions? No questions? Okay. Great. So then let's move on. Oh, there's a question? Okay, no questions. All right, so let's move on and talk about a new section, which is 3.10. And which is called linear approximations. Okay, so here's the basic idea. Suppose that you have a function f of x, and I'm going to take a point A, and I'm going to look at the tangent line of the function at that point. So we're going to start with a function f differentiable. Okay. This function, we're going to give it a name. We're going to call it L of x. Is the tangent line at the point A. Okay, so now, as you guys all know, the y-axis is the value of the function at the point. For example, at this point, if this point is, say, 3, then the vertical line is the function evaluated at the point 3. Right? So you can see from this graph, do you agree with me that the function L of x and the function f of x are pretty similar? at least around a, right? When x is close to a, when x is similar to a, the values of the function f and the function L are similar. Do you agree? That's it. That's the main idea. It's the main idea of linear approximations. The idea is to approximate a complicated looking function f with a simple function L, okay, because they have similar values. So note f of x is similar to L of x for x close to a. Okay, that's the main idea here. And the second ingredient of the linear approximation is to figure out a formula for L. Turns out that L has a pretty simple formula which you can calculate and learn. And then basically if you have a point x that is close to a, we can approximate it by this other function which is easy to compute. So let's do that. Okay, so now we're going to calculate the formula for L of x. Now, L of x is a straight line. Straight lines have usually pretty simple formulas. We've used this formula a few times already. What formula can we use to find out L of x? What equation? What is it?
Y minus y1 equal m times x minus x1.
Okay, y minus y1 equals m times x minus x1. That's right. This is what we call the point slope equation. We know that this line goes through the point contains the point A, comma. So this point right here is on the graph, right? On the graph of L. And that point has coordinates A, comma, what? A, comma, f of A. That's right. And what slope does it have? What is the slope of L? It's a derivative of f at the point A, right? Great. Now, you guys should know this formula by now because we've used it a few times, but what is the point slope formula? The point slope formula says y is equal to y0 plus m x minus x0. Before we used to write it the other way around, m times x minus x0 plus y0. It's the same thing. So where, of course, x0 and y0 are the points that the line goes through, and m is the slope. So in this case, L of x is equal to y0, which is f of a, plus the slope, which is f prime of a, multiplied by x minus x0. And x0 is what?
A.
X0 is a. So there you go. We have a formula for x, for L of x. Let's put all together. And that means that, therefore, that means that f of x is approximately equal to L of x, but L of x, we have a formula for it, is right here, is approximately equal to f of a plus f prime of a times x minus a for x near or close to a. That's the formula. That's the approximation formula. We call this linear approximation because we're approximating a nonlinear function or any kind of function with a line, with a straight line. Okay, so let's do an example of this. Example. Estimate. Estimate is the same thing as approximate. Estimate the square root of 4.1 using linear approximations. Okay? So this is a funny question because we're not giving a function yet. Right? We have a formula that involves a function and we don't have a function. So we have to think a little bit more. What function would be useful in this case? Right? So, and also what point A? We're not told a function and we're not told a point. In order to use this formula, you need a function and you need a point. So what do you think we should use for the function? Okay, well let's try that. F of x is square root of x. And what do you think we should use for A? Well, here's the thing, and this is it's an important part of the trick. We don't really know the square root of 4.1, but we know very well the square root of 4, right? So 4 can be thought of as some kind of anchor point where you can calculate everything, right? You can calculate f of x, and you can calculate the derivative also at 4, as we'll see in a moment. So let's try and set a equals 4. So what we want to compute, square root of 4.1, is nothing other than f of 4.1, right? Right? So that means that square root of 4.1 is approximately equal to, by this formula right here, to f of a plus f prime of a times x minus a. I'm sorry, where x is equal to 4.1. So there you go. That's the way to use this formula to estimate square root of 4.1. Now we need to plug in this information here. We need to plug in f of a and f prime of a. So f prime of x is equal to what? If f of x is square root of x, what is f prime of x? 1 over 2 square root of x. So what is f prime of a? Remember, a is 4, right? So it's 1 over 2 square root of 4, which is what? 1/4. That's right. Okay, and that's it. So then that means that square root of 4.1 is approximately equal to 2, which is square root of 4, plus 1 over 4, which is f prime of a, so f prime of 4, multiplied by 4.1 minus 4. And that is equal to 2 plus 0.1 divided by 4, which is equal to 2 plus 1 over 40. So there you go. We have now an approximation of square root of 4.1 using linear approximations. That's not actually equal to square root of 4.1, but it's very similar. Okay, so another concept that's related to this whole thing is something called differentials. I don't know what people are leaving. We still have 10 minutes to go. Okay, differentials. Here's the idea. suppose that you have a function f of x, okay, and we have a point A, and we have a tangent line at the point A. And that function is called L of x. Same as before, right? So let's suppose that we take a point x. And we're going to do this thing that we've done in the past a few times, which is that we call this distance right here, we call it delta x. Okay? So we make a small increase in the value of a to create x plus a plus delta x. So here we have delta x again. All right, and now this distance right here from here to here is delta y. Delta y is the difference between the value of f at this point and the value of f at this point. And we're going to take another distance that we're going to call, just to give it a different name, we're going to call that dy. So dy is the difference in the function L from this point to this point. All right? Let me write a formula for those two things. Delta y is equal to f of x plus delta x minus f of a is the actual difference between the two values, and dy has a much simpler formula, namely f prime of a times delta x is the estimated difference. Okay, we're basically doing the same thing with a different notation. Now, in terms of this notation, the main idea is that for x near a, the two things are actually very similar. Delta y is similar to dy. That's the idea. So you have an actual difference in f that you would, for example, might want to compute, and you have an estimated difference that is not the same, but is similar to the actual difference. Okay? So this is easy to compute. This is hard to compute, but more precise. So let me give you an example of what you could do this for. Suppose that we're measuring a circle. Okay? Say that you have a circle on the floor, and you're trying to compute the area of this circle as precisely as possible. And the way that you compute the area is by calculating the radius. So here's the radius, and the area of the circle is what again? Pi r squared, that's right. Okay, so now but think about it in these terms of errors, of error correction. So suppose that you figured that r is roughly equal to 10, but not exactly 10. It's 10 plus or minus 0.1 meters. Okay? So you don't know, you're not precise, your ruler is not perfectly correct, so there's an error bar, and you figure roughly my error bar is plus or minus 0.1 meters. Question, is estimate the error in the area. Okay, so how do we estimate the error in the area? Well, we're going to do the same thing as before, except that now the independent variable is not x but r, and the dependent variable is not y but a. So what used to be x, we're going to turn into r, and what used to be y, we're going to turn into a. So a of r is equal to pi times r squared. That means that a prime of r is equal to 2 pi times r. Now, a is equal to 10, and my delta r is equal to 0.1. Okay? So the error delta a, this is the actual error, is similar to my estimated error dA, which can be written as a prime of little a times delta r, and that is equal to 2 pi times 10 times 0.1. Right, because a prime of a is a prime of r is 2 pi times r, so a prime of a is 2 pi times 10. When you multiply by delta r, you get 0.1, and that is equal to 2 pi. That means that the area can be basically estimated as the original area, which is pi times 10 squared plus or minus 2 pi. That's it. You can estimate the error in a function if you have an error bar for the independent variable. Questions? Okay. All right. Great. So those of you who want to come this evening, see you this evening. Otherwise, good luck studying. See you on Friday.